Back. Today we're going to talk about solutions to linear time invariant systems. Okay, so just to set out a kind of quick agenda for what we're going to talk about today, we'll talk about solutions to continuous and discrete time LTI systems, and then we'll talk about how to compute some important quantities related to those. All right. In particular, we're going to focus a lot of time on constructing the Jordan form. Okay, let's get started. So before I jump into these two items, I actually just want to provide a kind of brief review of what we covered last time. Okay, so let's start with a quick review of last time. Okay, so we really had a couple of key results last time, right? If you remember in the previous lecture, a lot of what we focused on was constructing solutions to linear time-varying continuous time systems, okay? We found that a key tool that arose in this study, was something called the state transition matrix. Okay, so if you recall, what the state transition matrix is a matrix valued map phi of t comma t naught, which is the solution to the matrix initial value problem, defined x dot of t equals a of t, x of t, and initial condition x at t naught equals the identity matrix, right? So we defined this matrix initial value problem, and we said that the state transition matrix is the unique solution of this matrix initial value problem, okay? Evaluated at time t. All right, what else did we show? So we showed we can compute the state transition matrix with this fancy infinite series called the Peano-Baker series, okay? With the Peano-Baker series. All right? And just as a reminder, if you're to kind of write out the terms of the Peano-Baker series, what you would say is, I'll just write out the first two or three terms here. Phi of t comma t naught is calculated identity plus integral from t naught up until t, a of tau d tau, plus integral from t naught to t, a of tau, integral from t naught to tau, a of tau prime, d tau, and so on, right? We kind of continue stacking more matrix integrals in here. All right? So what this enabled us to do is we could construct solutions, unique solutions to the state equation of a linear time varying system representation, right? So if I give you the state equation of a linear time varying system, which is a differential equation, x dot of t equals a of t x of t plus b of t u of t, and I give you some initial condition, x of t naught equals x naught, and I assume that my input to this system is piecewise continuous, then what we showed is we can actually write out the solution to this initial value problem entirely in terms of the state transition matrix, okay? So in particular, what we had is that the solution evaluated at time t is given by phi of t comma t naught times x naught plus the integral from t naught to t, phi of t comma tau, b of tau, u of tau, d tau. All right? So this gives us the unique solution. And once we had this unique solution written down, what we were able to conclude is that a linear time-varying system representation yields a formal, I'll put formal in quotes, formal linear I/O dynamical system. All right, so this was one of our big goals of the second lecture, to show that these things actually give us formal dynamical systems. Okay, now that's the continuous time case. Let's talk about the discrete time case. Let's kind of quickly summarize some of the things that we said. So the discrete time case, what we could do is we could also define a state transition matrix. All right, so also define a state transition matrix. Okay, and just like above, how we defined phi of t comma t naught as the solution to a matrix initial value problem. In discrete time, we'll define phi of k comma k naught to be the solution to a matrix recurrence. All right? So if you went ahead and you kind of read a little bit about this discrete time case, what you would find is that the discrete time state transition matrix, which I'll denote phi of k comma k naught with square brackets, is the solution of the recurrence x at time k plus 1 equals a at time k, x at time k, and x at time k naught equals the identity. All right? So this really mirrors the continuous time case pretty closely, right? We're just swapping out a differential equation for a recurrence. All right, and once we have this, what you could do is you could find phi of k comma k naught via a product of matrices. All right, so if I wanted to calculate phi of k comma k naught, I could calculate the product a k minus 1, a k minus 2, all the way down to a of k naught. All right, and using this, you can compute solutions to state equations of a discrete time linear time varying system. Okay, so really you'll end up with a structure of formula that looks pretty much identical to this continuous time case up here. What you're going to do is you're really just going to swap out this integral for a sum, and you're going to swap out a real numbered time for an integer time step. Okay? All right, so that's kind of what we talked about last time, right? So last time. Now today, what are we going to do? Well, what we're going to do is we're going to focus in on the time-invariant case. Okay, so you might remember from lecture 1, when we, initially defined all of these system representations, we said that a continuous time system representation is time-invariant if each of those matrices in the representation is a constant matrix, right? So for instance, we have A, which is ordinarily a function of time, is just equal to some constant matrix A in Rn by n. B, which is also ordinarily a function of time, is equal to some constant matrix B. This will be in Rn by m. C equals a constant C in Rp by n. And D equals some constant D in Rp by m. Okay? And then discrete time, you do the same thing, right? You just say each of my sequences is now going to be a constant matrix A, B, C, and D. Okay? So the key question that we have to ask here is, what insight does this time-invariant structure yield? Okay? So above, we were able to say a whole lot about these time-varying systems, right? We came up with formulas for their inputs. We came up with formulas of their states based on their inputs, their initial conditions, times, all these sorts of things. Now we've made a pretty big simplifying assumption, right? We're saying each of these matrices is, just equal to a single fixed matrix. It never changes, right? The data of our system is time-invariant. So what does this actually buy us, okay? And this is what we're going to talk about today. So as we'll find out, this time-invariant structure actually gives us a whole lot, all right? There's a huge amount of new structure that we could use to our advantage. All right, so what I'm going to do is I'm going to start out with the continuous time case. So continuous time case. We're going to discuss here solutions to linear time-invariant continuous time systems. Okay, so let's set this up. So I'll say, first, what we'll do is, we know these state transition matrices kind of tell us everything we need to know about the system. So we'll figure out how the state transition matrix simplifies in the time-invariant case. Okay? So what I'll ask is if A, which is ordinarily a function of time, is equal to some constant A in Rn by n, how does the formula for the state transition matrix, right, for the continuous time state transition matrix, simplify. Okay. Well, we know we can kind of calculate the state transition matrix in general using the Peano-Baker series, right? So what I'm going to do is I'm just going to take in a constant matrix A, I'm going to plug it into this Peano-Baker series, and I'll kind of see how this problem simplifies. All right? So we know that, let me actually switch colors here. There we go. So we know that phi of t comma t naught is equal to the identity, right, plus integral from t naught up until t, now of a constant matrix A, d tau, plus integral of t naught up until t, constant matrix A, integral from t naught up until tau, a d tau prime, d tau, and so on, right? Okay. Now the nice thing is here, since these matrices are all just constants, we can actually evaluate these integrals. All right, let's go ahead and do that. So we'll get I plus a times t minus t naught. Little computation here. What we'll find is we'll get a squared times t minus t naught squared over 2. And if we kept going, the next term we would find would be a cubed t minus t naught cubed, not over 3, but rather over 3 factorial, okay, over 6. And this pattern would sort of continue, okay? So what I want you to do now is take a moment and see, do you recognize this pattern? Okay, take a moment to think about that. Okay, I'll assume that you've, kind of gotten your bearings. And maybe what you thought about after, kind of staring at this thing for a little while is that what this looks like is the power series formula for the exponential, right? But here we're really plugging in a matrix, right? So we're taking the exponential of a times t minus t naught, all right? So it's just as if we took this matrix a, multiplied it by time t minus t naught, and plugged that right into the power series formula for the exponential, all right? So we give this thing a very special name, all right? This is called the matrix exponential. Okay, so what I'm going to do is I'm going to define the matrix exponential on the set of complex matrices, okay? Now this is for the sake of generality. We'll kind of want the ability to take the exponentials of complex matrices for reasons we'll see a little bit further on in this lecture. Okay, here's what I'm going to do. I'm going to define the matrix exponential as a map exp on Cn by n, maps back into Cn by n. And what it does is it takes a matrix A and it maps it to the power series exp A equals I plus a squared over 2 factorial plus a cubed over 3 factorial, and so on, all right? So if we write this out as a full infinite series, what we'll get is that this is equal to the infinite sum from k equals 0 up until infinity, a to the k over k factorial, okay? So all that we're doing here is we just take a, plug it into the power series formula for the exponential. All right, nothing more than that. Okay, so what next? Well, there's something that we always really have to do, right, whenever we kind of write out some infinite series. And the first thing that we need to do is we need to make sure that this infinite series actually converges, okay? So let's go ahead and confirm that exp A actually converges. And the nice thing that we'll find is that we actually get a stronger mode of convergence called uniform convergence, all right? This is just like we had with the Peano-Baker series. Okay, here's what we're going to say. Let me state this as a proposition. Oops. Proposition, convergence of the matrix exponential. So what I'll say is take a matrix in Cn by n, then for any time t prime, which is greater than or equal to 0, the series x of a times t, which we defined above to just be a to the k t to the k over k factorial, right? We sum from k equals 0 up until infinity. This series converges uniformly on minus t prime comma t prime. All right? So what we're saying is take any compact interval that we want. This matrix exponential will converge uniformly on that compact interval. Okay, so let me sketch out a proof for this real quick. The nice thing is, because the matrix exponential is actually just a special case of the Peano-Baker series, right? Like we kind of sketched out above, in the case of a real matrix, we don't actually have any more work to do. Okay? You might remember last time we actually already proved the Peano-Baker series converges uniformly on any such interval. Okay? So there's really nothing new that we need to do here for the exponential. Okay? So for a and Rn by n, just reduces to Peano-Baker series. Okay? Now here we state this for a and Cn by n, which is technically something that we haven't yet proven, but really the proof is identical. Okay? So I just won't cover it here. So proof is identical. So if you're interested in a direct proof of this result, I would encourage you to give it a try. It's really just the same thing as the Peano-Baker series, okay? If not easier. All right, so we've defined the matrix exponential, right? Now what we want to do is, maybe we want to establish a couple of basic properties, okay? So properties of the matrix exponential. What I'll say is let A belong to Cn by n. Then the matrix exponential satisfies the following. So first, what we have is if lambda comma v is a pair of eigenvalue and eigenvector of A, then take a moment to guess what you might have for the matrix exponential. Okay, so what you'll have is e to the lambda, and the same eigenvector v is a pair for x of a. All right? Now second, you have a kind of nice condition on the determinant. So what you could prove is that the determinant of the exponential of a is equal to e to the trace of a. All right? So this is a kind of nice fact. Something that this actually tells us is that the matrix exponential is always invertible. All right? That leads us on to the third point over here, which is x of a is invertible with inverse x of minus a. All right? So I'll leave this proof to you. So this proof will actually show up on your homework too. Okay? So you'll go ahead and you'll kind of get acquainted with the matrix exponential in there. All right, great. So now we've kind of talked about a couple of basic properties of the matrix exponential, right? We have convergence guaranteed. We have a couple of basic nice properties. Now let's just go ahead and confirm that, it actually gives us what we want for a linear time-invariant system. All right? I'll just state this as a proposition, which is the state transition matrix of linear time-invariant system. Okay, so I'll say let A belong to Rn by n. The continuous time state transition matrix with respect to A is computed phi of t comma t naught equals x of a times t minus t naught. Okay, so you exactly compute this thing with the matrix exponential. In other words, x of a times t minus t naught is the unique solution to the matrix initial value problem defined x dot of t equals constant matrix A times x of t, and x of t naught equals the identity. Okay? And the proof of this is just apply Peano-Baker series. Okay? We've actually already done all of the work for this in the previous lecture. We just have that the Peano-Baker series reduces to the matrix exponential when we have a constant matrix. All right, and that's a proof. Okay, very nice. So what we've done now is we've shown that, this matrix exponential actually equals the state transition matrix for a linear time invariant system. All right, and what this means is that we can calculate solutions to the state equation of a linear time invariant system in terms of the matrix exponential. All right, so if I just go ahead and I refer to these formulas from up here, right, where did I put them? Here it is. So if I just take this formula up here, and every time I see this kind of black box phi of t, t naught, I can just replace it with a matrix exponential, right? Exp of a, exp of a of t minus t naught. Okay, so I'll just do that right now just so you can see what it looks like. All right, so what we have is that the solution to the initial value problem, x dot of t equals a times x of t plus b times u of t with an initial condition x of t naught equals x naught. It's going to be given by the formula x of t equals e to the a t minus t naught times x naught plus the integral from t naught up until time t, e to the a times t minus tau, bu of tau, d tau. All right? The proof of this is literally just the Peano-Baker series reduces to the matrix exponential. Okay, so I want to emphasize we already did all of the heavy lifting for all of these results last time, right? Now it's just as easy as Peano-Baker series becomes matrix exponential. Okay, so that gives us a treatment of the continuous time case. Now I want to talk a little bit about the discrete time case. All right, so once again, the discrete time theory is really quite similar to the continuous time theory. The only thing that we're going to do here is we're going to have a recurrence instead of a differential equation, okay? And instead of a matrix exponential, what we'll find is that we have a matrix power, all right? So you might remember from earlier, right, just above, I said phi of k comma k naught for a general discrete time linear time varying system is going to be computed a k minus 1 all the way until a at time k naught, all right? So in the time invariant case, all of these matrices A are identical, right? What that means is that phi of k comma k naught will actually just reduce to a to the k minus k naught, right? And just as a quick sanity check, what you'll have over here is phi of k naught comma k naught equals a to the 0 equals the identity, all right? So that kind of tells us that we haven't made any major mistakes here, right? If we don't have any time pass, we stay in the same position. All right, fantastic. So what you could do is once you have this kind of nice formula for the discrete time case, you can compute solutions to your discrete time state equation. All right, and what you have is really the same thing as the linear time varying case, right? What we're going to do is if we want to translate from continuous to discrete time, what we'll do is we will swap exponential for raising to the power k, and we'll swap the integral for a sum. And if we do these two things, we'll arrive at something that pretty much resembles the formula for the discrete time case. Okay? So if you're interested in the particular formula, you can see the notes. All right, so let's kind of summarize some key takeaways from this. All right? And one of the things that you could find is, just by a little bit of work, you can now prove that a linear time invariant system representation actually yields a formal linear time invariant dynamical system. All right? So this is one of the major things that we needed to make sure that our theory was consistent, right? That our LTI representations actually give us LTI dynamical systems. All right, fantastic. So let's actually go ahead and talk about computing exp of at and a to the k. All right? And this is where we're going to spend the remainder of our lecture. All right? It turns out this is actually a kind of hard problem to solve. So here's what we have so far. Where at? Okay? So what we showed above is you can compute the continuous time state transition matrix via the exponential x of a t minus t naught, right, in the continuous time LTI case. And you can do something similar for the discrete time case, right? Phi of k comma k naught is equal to a to the k minus k naught for discrete time LTI. Okay, and these things are nice, but can we actually compute them? Okay, so things kind of seem to have simplified significantly, but the problem is I've taken one infinite series, right, the Peano-Baker series, and then I've just handed you another infinite series, right, the exponential. Okay, so let's kind of make sure that we haven't really shortchanged ourselves here. All right, we got to make sure that we can actually compute the matrix exponential and compute any power of a in order to make sure these simplifications are actually useful for us. Okay, so let me highlight a goal. And our goal of the rest of this lecture is to actually compute exponential and a to the k in closed form. Okay? So what this means is for the exponential, I should have no more infinite series remaining, right? Everything should be concrete. And for a to the k minus k naught, I should have no matrix powers remaining. Okay? So I want to compute these things in closed form. All right, so let's kind of figure out, what a nice method of doing this might be. So I'm going to start with the discrete time case, because it's a little bit easier, right? So what do we know about computing a to the k? All right, well, in general, there's no nice formula for directly computing the power of a matrix. Right, if I just hand you a matrix and I say, give me the kth power of that matrix, that's not something you can immediately do, right? You'll at least have to do a little bit of work before you can compute that. But, there's this kind of powerful idea where if we transform this matrix into a different coordinate system, we might figure out a new matrix that's kind of easier to compute the exponent of, okay? So our basic idea, instead of just kind of computing a to the k straight up, what we'll do is we will transform and compute. Okay? So this will be our key strategy in this section. First, we change coordinate systems into a new coordinate system where an exponent is easier to calculate. We calculate the exponent in that easier coordinate system, and then we switch coordinates back. Okay? So there's a couple things that we need to confirm to make sure that this is actually a well-posed idea. All right, what we need to do is we need to confirm that transform and compute is well posed for exponents of a matrix. Okay, now we'll go ahead and we'll confirm this in the following lemma. So lemma is going to be called similarity transforms and matrix powers. And what this lemma essentially says is that for A in C n by n and an invertible T in C n by n, what we have is for all k greater than 0, where k is some integer, T inverse AT to the k is equal to T inverse A to the k times T. All right? So let me just kind of summarize what this is saying. This is something called a similarity transform of a matrix, right? You might remember that's how we actually compute changes of coordinates of matrices. And what we have is that if we compute the kth power of the similarity transform, that's the same thing as computing the kth power of this inside matrix and then doing our change of coordinates, okay? So this essentially tells us that this idea of transform and compute is very well posed, right? If we want to take the kth power in some nice coordinate system, that's something that interacts easily with kind of these matrix changes of coordinates. Okay, so let's go ahead and prove this result. All right, so proof. This proof will follow by induction. So the base case, you have k equals 0. What you have is T inverse AT to the 0 is just equal to the identity, right? And T inverse A to the 0t is equal to T inverse times the identity matrix, oopsie, T inverse times the identity matrix times T, which is equal to T inverse times T, which equals the identity, okay? So in the base case, these two things are equal to each other. Now we'll assume for the inductive step that will seem true for some k greater than 0, okay? And then what we'll verify is T inverse AT to the k plus 1 satisfies this property, right? First, we'll just break this up. This is T inverse AT to the k times T inverse AT. Now we'll multiply out. What we have left is, if we imply the inductive hypothesis to this guy, this is equal to T inverse A to the kt. Now multiply by this, T inverse AT. That becomes the identity, right? T inverse A to the k, identity, times A times T, which is equal to T inverse A to the k plus 1 times T. Okay? So that proves this result by induction on k. Right? First we showed it for the base case, then we show it for the inductive step. Okay, nice. So what this lemma does is this lemma confirms that coordinate change or similarity transform and exponentiation interact well. All right, now that I've shown that coordinate change and exponentiation kind of interact well with each other, I want to give you a quick example of how we can use this property to our advantage. Okay. All right. So what we'll find is that matrices that are diagonalizable have a particularly nice structure under exponentiation. Okay. So I'll prove this to you next. So proposition, which is a power of a diagonalizable matrix. Okay, what I'll say is let A, which is a matrix in Cn by n, be diagonalizable. All right, so remember, what this means is that there exists some matrix T in Cn by n, which is invertible, such that T inverse A times T is equal to a diagonal matrix, which I'll denote diag lambda 1 through lambda n. Okay, so just to clarify, what we have is T inverse AT is equal to the diagonal matrix lambda 1 through lambda n. Right? There's zeros everywhere else in this matrix. Okay, then what we have is, for all integers k greater than or equal to 0, A to the k is computed, T times diag of lambda 1 to the k through lambda n to the k multiplied by T inverse. Okay, so we actually get a nice closed form solution for what A to the k is in this case. All right, so the proof, first you could go ahead and compute what the exponent of a diagonal matrix is. What you would find after a little bit of algebra is diag of lambda 1 through lambda n, all raised to the k, is equal to diag of lambda 1 to the k, lambda n to the k. All right, so now that we've established this, all that we need to do is apply our previous proposition. What this tells us is that T times diag lambda 1, lambda n, T inverse to the k is equal to T times diag of lambda 1 through lambda n to the k times T inverse, which is equal to T times diag of lambda 1 to the k through lambda n to the k T inverse. All right, since this guy over here was equal to A to the k, we have our result. All right, so A to the k equals this to the k, then we could pull out T and T inverse using the previous results, and then exponentiate using this nice rule for the exponential of, for the exponent of a diagonal matrix. Okay, nice. So this gives us a nice way of computing any power of a diagonalizable matrix, right? First we diagonalize, we compute the exponent of the diagonal matrix, and then we change coordinates back to our original coordinate system. Okay, so this kind of verifies this nice transform and compute idea in discrete time. Okay, so let's talk about the continuous time case. Continuous time case. What we want to do now is we want to get started on computing exp of at in closed form. Okay, or actually, we'll just stick with exp of a for now, right? This will cover exp of at as well, right? We just multiply a by an at, and then we're pretty much good to go. All right, so the first idea that I want to illustrate, this is kind of, maybe an obvious guess, is one might wonder if the exponential of any matrix A, entry ij, is equal to exponential of a comma ij, right? It's kind of natural to wonder, if this exponential works element-wise, right? If I take the exponential of my entire matrix, do I just get something which is e to each entry of that matrix? And the answer is no, right? This is not true at all. Okay, and a quick counterexample. If I go ahead and I take the exponential of the identity matrix, the 2 by 2 identity, what I'll find is that I will get e to the first, 0, 0, right? But if I was just to take e to the first, e to the first, e to the 0, e to the 0, which is what I would do if I got element-wise, I would get something that's entirely different, right? So these are not the same. Okay? So element-wise computation is not something we could do for the matrix exponential. All right? So element-wise does not work. Okay? Since element-wise doesn't work, let's try this transform and compute method. Okay? So remember, what we first did when proposing this transform and compute method for the discrete time case is we checked that transform and compute behaves well under exponentiation. Okay? So we took a similarity transform of a matrix and we found that that interacted very well with taking a power of the matrix. Now we need to do the same thing for the exponential, right? We need to verify that the matrix exponential works well with different transformations of our given matrix. Okay, let's go ahead and do this. Let me state a proposition. So proposition, which is similarity transforms and the matrix exponential. Okay, so what I'll say is let A be a matrix in C n by n. Oops, let me redraw that. C n by n. And T in C n by n be an invertible matrix. Okay, so just to clarify, I'm only assuming T is invertible, right? I'm not assuming anything about A. And then what I have is exp of T inverse AT is equal to T inverse exp of A times T, all right? So we get something that looks really kind of similar to the case of a matrix power, but now for the matrix exponential, right? I could essentially just pop out a similarity transform, compute the exponential, and then reperform this multiplication. All right, let's go ahead and prove this. What I'm going to do is I'm going to start with the partial sums of the exponential. Okay, so I'm not going to look at the whole infinite series because we might have some convergence issues. I'm going to start just by looking at the first p terms of the series. Okay, so if I evaluate sum from k equals 0 up until term p of T inverse AT to the k over k factorial, what I'll get using that rule that we derived above is that this guy is equal to T inverse k equals 0 to p a to the k over k factorial, all multiplied by t. Okay? So can we pass to the limit? So can we pass to the limit as p goes to infinity? All right? So this isn't something we can always, immediately say is true, right? We need an assumption that t acts on, this expression inside here continuously. Okay? So what we have is, since matrix multiplication is continuous, you can actually posit the limit. And what this tells us is that the limit as p goes to infinity of this material over here, right, is equal to t inverse times the limit as p goes to infinity of this term, right, times t. And that, in fact, confirms that x of t inverse at is equal to t inverse x with a times t. All right, that's a proof. So just as a quick clarifying remark, what we have is that for a continuous function in a convergent sequence, we have the limit as n goes to infinity, f of xn equals f of limit n goes to infinity xn. Okay? So the key fact here is that matrix multiplication is continuous, so this is a rule that we can apply. Okay, fantastic. All right, so now that I've shown that the exponential interacts well with changes of coordinates, what I'll do is something similar to the discrete time case, right? I'll produce a nice change of coordinates in which we can actually compute this exponential in closed form. All right, so I'll state this as a proposition. Once again, we're going to find that diagonal matrices are super easy to compute things for. Okay, so proposition, the exponential of the diagonalization. Okay, and what this says is let A and Cn by n be diagonalizable. Right, so remember this means there exists a t in Cn by n for which t inverse at equals diag lambda 1 through lambda n. Then what we have is the exponential of a is equal to t times diag e to the lambda 1 e to the lambda n times t inverse. Okay? So taking the exponential of a diagonal matrix, or excuse me, of a diagonalizable matrix is really something that's quite easy to do, right? We just compute its diagonalization, we take e to each element of the diagonalization, and then we change coordinates back. Okay? And the proof of this is really just a straightforward application of this previous result that we just proved, and then the one before it, right? Which tells us diagonalizable matrices have nice formulas for exponents. Okay? So the proof is just apply the two previous results. Okay? And then this should follow pretty straightforwardly. Okay, so what I've done so far is I've shown that this transform and compute method, transform and compute, works pretty well. Okay, so we showed that if we transform our matrix into a diagonalizable, or excuse me, into a diagonal form, we compute either some matrix power or the matrix exponential of that diagonal form, we can easily recover either the power or exponential of our original matrix, right? There's only kind of one problem with this. I'll ask this in the form of a question. Is every matrix diagonalizable? And the answer, no, right? Of course not. Couldn't be that easy, right? So let me give you an example, right? If you take the matrix A equals 1, 1, 1, and 0, this is not diagonalizable. So the basic problem here is diagonalizability is too strong a condition. Okay? If we want to figure out a way to compute either a matrix power or a matrix exponential of any matrix, right, it's too much to ask that that matrix be diagonalizable. So what we need to do is we need to relax diagonalizability to something easier, right? Something that's easier to satisfy, that still has predictable structure. nice structure that we kind of know how to solve for in closed form under exponentiation, right? Either raising something to the power or taking its matrix exponential, okay? So what then would be a natural relaxation? So what is a natural relaxation of diagonalizability? Well, let's start by talking about what a natural relaxation of just something being a diagonal matrix is, right? Then we'll find out, an equivalent version of diagonalizability, right? Well, if we kind of look at, the structure of a diagonal matrix, maybe instead of asking that our entire matrix be strictly diagonal, we can ask that it be broken up into diagonal blocks, we can ask that it be broken up into a diagonal structure of blocks, all right? This is something called a block diagonal matrix. So definition, which is a block diagonal matrix, all right? So instead of asking that our entire matrix be diagonal, we're going to ask that it has some sort of, general block diagonal pattern, okay? So what we say is that a matrix D in Cn by n is block diagonal if there exist matrices lambda I in Cni by Ni, where I goes from 1 up until some number p, such that all of these dimensions Ni to p sum up to the total dimension of our space, and what we have is D equals lambda 1 through lambda p, right? With zeros everywhere else. Okay, so a matrix is block diagonal if we can write it in this block structure, right? So each of these lambda 1s through lambda p's is actually a matrix itself, right? So we have a block diagonal structure. Each of these individual blocks could have any structure out there, right? We don't enforce that they be diagonal, all right? So if we have that a matrix is a block diagonal with blocks lambda 1 through lambda p, then what we'll write in general is that D equals BLK diag, or block diag, of lambda 1 through lambda p. All right, so this is generally how we'll denote that D is block diagonal of this form. All right, fantastic. So this is really a nice relaxation of the idea of diagonal, right? Instead of asking that our actual matrix is diagonal, we're just asking for some much looser diagonal structure. Okay, now the key property is that since we still have some diagonal structure, similar exponentiation rules apply to the block diagonal case. All right. In particular, what we'll find is that if D equals the block diagonal of lambda 1 through lambda p, and we take some number, which is an integer, k greater than 0, then what we have, greater than or equal to 0, is D to the k is equal to block diag of lambda 1 to the k all the way to lambda p to the k. Okay, so exponentiating a block diagonal matrix is the same thing as just exponentiating each individual block. Okay? All right, nice. So the proof, this is just a nice exercise in algebra. Okay? There's really nothing much to the proof. All right, so give this a try if you don't believe me. All right, so what we've done over here is we've confirmed that we get a predictable structure under exponentiation for a block diagonal matrix. All right, nice. Okay, so we've established that we get a nice structure under exponentiation for a block diagonal matrix. Are we done? Well, if we take a look at this formula up here, right, what we find is that we actually need to know how to compute the exponents of these blocks, right? So it's not good enough just to have a block diagonal matrix. What we need is that the blocks themselves should be easy to compute exponents of. Okay, so we'll require a specific structure on the blocks in addition to a specific structure on the actual matrix itself. Okay, so what kind of structure might we look for? Well, obviously we got to rule out diagonal structure right away, right? Because then our matrix D is just going to be a diagonal matrix, and that's exactly the problem we were trying to avoid, right? So what we'll try instead is we'll get something that is as close as possible to diagonal. All right. Now, obviously, this is a little bit subjective, but what we'll do is we'll take what would ordinarily be a diagonal structure, and we'll just add a super diagonal, right? This area right above the diagonal, we'll add a super diagonal of 1s, okay? And there will be 0s everywhere else in the matrix. This gives us something called a Jordan block. Okay, so definition, Jordan block. So what I'll say is let lambda belong to C. The Jordan block of size n corresponding to lambda is the matrix J equals lambda times I, where I is the n by n identity matrix, plus n naught, all right? Where n naught is the matrix defined as 0, 0, all along the diagonal, right? 0 is below the diagonal, and then 1s just above the diagonal, right? And we'll have 0s elsewhere, okay? So what that means is that J is going to look like the following. So it's going to almost be a diagonal matrix, right? We'll have lambdas along the diagonal, but then just above the diagonal, we'll have 1s, okay? So this is called a Jordan block of size n, if this is in Cn by n. Okay, so let me highlight something over here. The structure of the Jordan block as a sum, J equals lambda I plus n naught, makes its exponents easy to compute. Okay, so first up, we know how to compute exponents of lambda I, right? Super easy. Okay, so if I take lambda I and I raise it to the k, that's just equal to lambda to the k times I. Now it turns out n naught, this matrix with 1s on the super diagonal, also has easy exponents. So also has nice exponential structure. All right, so let me explain now exactly what this structure is. So lemma, exponents of n naught. Okay, so I'll say let n naught in R, oops, I'll just say Cn by n, why not, be the matrix above. Its exponents respect the sequence as follows. So first, we just take n naught to the first, then we just get the actual matrix, right? 0s, 1s. Now if I take n naught to the second, what we'll find is that this super diagonal of 1s actually shifts up to the right by 1, okay? So if I go ahead and I compute n naught to the second, then I'll get 0s, 0s just above the diagonal, and then above this kind of super diagonal of 0s, I'll get a bunch of 1s, all right? And there's 0s elsewhere. And this pattern continues of this kind of super diagonal of 1s shifting up by 1, right? Shifts 1 up for each new exponent that we take. This continues all the way until we go to n to the n, at which point we get the 0 matrix, right? So at this point, this final 1 is kind of kicked out of the matrix, and we're just left with all 0s everywhere. Okay, so what we have is for each successive exponent, the diagonal of 1s shifts 1 to the right. Okay? So this is very predictable. What this essentially tells us is that for any number k, right, for any k greater than or equal to 0, we know how to compute n naught to the k, right? If k is strictly less than n, then we use the shift rule. And if k is greater than or equal to n, it is 0. Okay? So this gives us a really nice, easy way of computing the exponents of this matrix, right? And just as a quick side note, n naught is an example of something called a nilpotent matrix. Nilpotent matrix. All right? So a nilpotent matrix is a matrix n such that n to the k equals 0 for some k greater than 0. Okay, so this kind of just explains the choice of letter n when we're defining n naught up here. All right, fantastic. So now what we know is we know we can compute any exponent of lambda I, and we know we can compute any exponent of n naught. All right. Putting these two things together, we can go ahead and compute the exponent of any Jordan block. Let's go ahead and do that right now. So proposition, exponent of a Jordan block. So what we'll have is we'll take a Jordan block, let j equal lambda I plus n naught. Then for all k greater than or equal to 0, what we have is j to the k is computable via the formula sum j equals 0 up until k of k choose j, lambda to the k minus j times n naught to the j. Okay? And the proof of this formula might seem a little bit mysterious, right? But this proof is actually just the binomial formula. So binomial theorem, right? What the binomial theorem says is that we have a to the b to the k, then this is equal to the sum j equals 0 to k choose j, a to the k, b to the, oopsie, k minus j, b to the k. All right, so all that we're doing here is we're just plugging in lambda I and n naught, and then the result follows. Okay, fantastic.